In this video, I want to do a pretty thorough examination of an example of particle motion. And so we see that a particle is moving along the x-axis. So he's moving to the right, he's moving to the left, maybe he's hanging out at a certain spot for a while. And we know that the velocity of this particle can be modeled by the function t squared minus 8t plus 15. And in this problem, we're going to be concerning ourselves with the interval time t equals 0 to time t equals 9. Okay? And we also have one more piece of information. We have an initial condition. We know that the position of the particle at time t equals 3 will be 8. Okay, so let's go ahead and get started. The first thing we'd like to do is to find functions for the position and the acceleration of our particle. Well, the acceleration function won't be too bad, because to move from velocity to acceleration, I just need to differentiate. So let's take the derivative of this. So the derivative of t squared is 2t, and the derivative of negative 8t is negative 8, and the derivative of our constant 15 is just 0. Okay? And how about a position function? Okay, so x of t is going to be our position on the x-axis. Well, to go from velocity to position, I need to integrate, okay? So to integrate this, let's see, I'm going to integrate my velocity function with respect to t, and that's going to be my position function. Let's go ahead and write that down. So let's go ahead and integrate t squared minus 8t plus 15 with respect to t, and that'll be my position function. So it looks like I'll have 1/3 t cubed minus 4t squared plus 15t plus c. Okie dokie. Well, this is nice because I actually have this initial condition that I can use. So let's go ahead and plug 3 in for my t value and then set that equal to 8. So I'll have 1/3 times 3 cubed minus 4 times 3 squared plus 15 times 3 plus c, and that equals 8. Okay, so now it's just some number business. 3 cubed is 27, divided by 3 is 9. 3 squared is 9 times negative 4, so minus 36. And then 15 times 3 is positive 45, plus c equals 8. Well, let's see. Negative 36 plus 45 is 9. 9 and 9 is 18, plus c equals 8. Let's go ahead and subtract 18 from both sides, and we see that our constant here is going to be negative 10. Okay, so this c value then is negative 10, so let's go ahead and write now our final position function, which I actually don't think will fit in this spot right there, so let me rewrite and move it over just a little bit. Okay, well, that's why we don't write in pen for math. Okay, so we have 1/3 t cubed, and let's see, minus our 4t squared plus 15t minus 10. Okay, so here are our three functions. The velocity function was given to us. We have the acceleration function and the position function for our particle along the x-axis. Okay, so the next thing, let's go ahead and talk about some specific velocities and accelerations, and then we can move into finding the intervals on which the particle is speeding up or slowing down. So let's go ahead and start with finding a couple of values. Let's say v of 2 and a of 2. What this means we're looking for is the velocity of our particle at time t equals 2 and the acceleration of our particle at time t equals 2. So let's go ahead and plug 2 into our velocity function. So I should have, let's see, 2 squared minus 8 times 2 plus 15, which will give me 4 minus 16 plus 15, which looks like 3. And our acceleration then, let's put 2 into our acceleration function. So 2 times 2 minus 8 is 4 minus 8 is negative 4. Okay, so what can I say about the particle when at time t equals 2 his velocity is positive, which means he's moving to the right, but his acceleration is negative, which means he's being pushed to the left? Well, I can say that he's slowing down because the force of this acceleration is going to be against his motion. So I can say at time t equals 2, the particle is slowing down because, and there are a couple of ways you can say this. You can either say because the sign of the velocity and acceleration at time t equals 2 are opposites, or you can say, let's see, it's slowing down because v of 2 is positive, but a of 2 is negative, so greater than 0, less than 0. Okay? So let's go ahead now and consider one more time. Let's say time t equals 6. So let's find v of 6 and a of 6, and then we'll compare those as well. So for our velocity function, let's go ahead and plug 6 in. Okay? So it's going to be 6 squared minus 8 times 6 plus that 15. So 36 minus 48 plus 15 looks like, what, 3 again? And the a of 6, we're going to be plugging 6 into our acceleration function. So 2 times 6 minus 8 is 12 minus 8 is positive 4. Okay. So here we see at time t equals 6, the velocity is positive, so he is moving to the right. Also, the acceleration at time t equals 6 is positive, so he's being pushed to the right. Okay, well, if he's being pushed in the same direction that he's moving, I'm going to say then at time t equals 6, the particle is speeding up because, and we have, let's see, v of 6 is positive and a at 6 is positive. So they have the same signs. Okay, let's kind of box that off as well. And let's generalize this. So we just kind of looked at two specific examples. Let's generalize and find, well, when in general between time t equals 0 and times t equals 9 is our particle speeding up and when is it slowing down? Okay, so I'm going to go ahead and draw a nice continuum here. So here is our number line, and we're starting at time t equals 0, and we're going to move up to times t equals 9. Okay, so 0 to 9. And I'm going to kind of model the velocity function on top and the acceleration function on bottom. And so I need to find where each of these equals 0 so I can plot those critical points, and then I can work with some test points and figure out the regions that are, positive or negative. So once again, let me write this velocity function down. We have t squared minus 8t plus 15, and I want to know when that's 0. Well, this actually factors pretty nicely down to t minus 3 and t minus 5. So we can say that at time t equals 3 and 5, we have 0. So let's go ahead and plot those 2 points. We have 3 and 5. And I'm going to do a little division here, kind of draw some lines. There we go. So we have 3 distinct regions here. We have from 0 to 3, 3 to 5, and 5 to 9. And the reason is, again, because our critical points are 3 and 5, so that's going to divide up our velocity function. Okay, well, our acceleration function, remember, was 2t minus 8. So when does that equal 0? Well, when 2t equals 8, or t equals 4. Okay, so I'll put that particular point in there as well. And I'm going to divide up our acceleration region into, well, we have 2 distinct regions, from 0 to 4 and 4 to 9. Okay, so we need some test points to figure out whether they're positive, negative, that kind of thing. Well, we actually already have a couple of examples. We have the velocity at 2 and the acceleration at 2. And we know that at 2 the velocity was positive. So let's put a positive right there. And we know at 2 the acceleration was negative. So let's put a negative right there. Similarly, we had the velocity at 6 was positive. So I can put a positive there. and the acceleration at 6 was positive, so I can put a positive there. So it looks like our two examples didn't go to waste. We got some information out of them. The only piece that we still need is, what about our velocity from 3 to 5? So let's just go ahead and find out what the velocity is at 4 real quick. So that'll be 4 squared minus 8 times 4 plus 15. So 16 minus 32 plus 15, looks like 31 minus 32. That's a negative. Okay, so we have a lot of information right here, and I like this. So we had our number line from 0 to 9, and we marked some critical points. We had 3 and 5 based on the critical points from our velocity, and we had 4 based on the critical point from our acceleration. And we know that our velocity is positive from 0 to 3, and again from 5 to 9. So you could say the particle is moving to the right from time t equals 0 to time t equals 3. And the particle is moving to the right also from time t equals 5 to t equals 9. Thus, the particle is moving to the left when it's negative, and that's from 3 to 5. All right, well, the acceleration, so we're being pushed to the left from 0 to 4, and being pushed to the right from 4 to 9. So when then is my particle speeding up, and when is it slowing down? So speeding up, slowing down. Okay, so it's going to be speeding up whenever the sign of the velocity and the acceleration are the same, either both positive or both negative. Well, we start out here with opposite signs, but then it looks like from 3 to 4 our velocity is negative and our acceleration is also negative. So it looks like we're speeding up from 3 to 4, and then they both are positive. It looks like the velocity changed at time t equals 5, and the acceleration is already positive there. So it looks like from 5 to 9. Okay, so it's speeding up at these t values from 3 to 4 and 5 to 9. Similarly, it's slowing down when the signs are opposites. So here we have positive and here we have negative, and that occurs from 0 to 3 before the velocity changes to negative. So we can say 0 to 3 it's slowing down. It looks like it's also slowing down when the velocity is negative here and the acceleration is positive, just for a moment between 4 and 5. So we could say 4 and 5. And let's see, that looks like that all of it, because then we have the same signs here. So are all of our intervals accounted for? Well, 0 to 3, 3 to 4, 4 to 5, 5 to 9. Yep, so all of our intervals are accounted for. The particle is either speeding up or slowing down. Okay, so I'm kind of out of paper here, so let me start a fresh piece, and I want to talk about the displacement versus the total distance traveled next. Okay, so let's go ahead and rewrite our velocity function. V of t was t squared minus 8t plus 15. And so let's talk now about displacement and total distance traveled. Well, the displacement concerns itself with, where was it at the beginning? Where was it at the end? How far away is he? So you can write this a couple of ways. So you can use an integral, and you can say, again, because our interval is from 0 to 9, so you can say the displacement is the integral from 0 to 9 of our velocity function with respect to time. Okay, but you'll notice in doing so, all we're really doing is finding this integral, which really is our position function, and then we're going to take and plug in 9 and plug in 0 and subtract. So another way you could say this is the position at 9 minus the position at 0. Well, this was nice because we were able to find the position function exactly because we had a nice initial condition given to us, but this isn't always the case. So if you're able to write the position function, this is definitely the way to go. If you're not, because you don't have an initial condition, well, this is definitely the way to go. Okay, so let's work this first, and then we'll visit the total distance traveled. Okay, so I'm going to rewrite this integral here from 0 to 9 of our t squared minus 8t plus 15 with respect to time. Okay, so the integral here is going to be 1/3 t cubed minus 4t squared plus 15t, and we're doing that from 0 to 9. Okay, so let's plug this 9 in again. So 9 cubed is 729. So it's 1/3 of 729. And then minus 4 times 9 squared, which is 81. And then plus 15 times 9. And then we're taking that and subtracting when I plug 0 in, but 0, 0, 0. That's just going to be a 0 anyway. So really all I'm concerned with is just evaluating that, and this is going to be my displacement. Okay, so 1/3 of 729 is going to be 243. And then 4 times 81 should be 324. And then 15 times 9 is, 135. So putting that all together should give us, let's see, 54 units, or just 54. So that means from the beginning, time t equals 0, to the end of our interval, time t equals 9, the displacement of our particle was 54 units. So he's 54 units away from where he started. But that doesn't account for maybe he turned around and went the opposite way for a while and maybe turned back around. So that's where the total distance traveled comes into play. So the total distance traveled, remember, is going to be the integral from 0 to 9 of the absolute value of our velocity function with respect to time. So here's the key difference. The displacement is just the integral of our velocity. The total distance traveled is the integral of the absolute value of our velocity. And it takes into account, the total distance traveled does, anytime the velocity changes sign. Okay? So what we need to do is we need to figure out, well, where does this velocity function change sign? And we kind of know that already because v of t, which equaled this t squared minus 8t plus 15, we factored that earlier down to t minus 3 and t minus 5. And so we knew that time t equals 3 and 5 were some major values. And we also knew that from 0 to 9, let's see, we have 3 and 5, our velocity function, let's see, was positive and then negative and then positive. So he turned around right here at time t equals 3, and he turned back around at time t equals 5. So he's traveling all happy to the right, turns around for a while and goes left, and then stops, turns around a while and goes right again. So the total distance traveled needs to take into account all of these things. So what it needs to do is really take the integral from 0 to 3 of our velocity function. It needs to subtract from 3 to 5. And the reason we need to subtract is because it's negative, and the two negatives make a positive. And then we're going to add back the integral from 5 to 9 of our velocity. Okay. Well, doing all three integrals and then evaluating at 0, 3, 5, and 9, it seems a little cumbersome. So instead, what we're going to do is just take our displacement, which we already have the value for, except the displacement did not take into account this right here. It actually subtracted it out. So I need to undo that to even out and find the 0 to 3 and 5 to 9, and then I need to do it again in order to add it back to my total distance traveled. So what I can do is say from 0 to 9 and then minus 2 from 3 to 5. Okay, and that will give me my total distance traveled. And again, there's other ways that you can do these absolute value integrals. I'm going to do it this way because we've already worked our displacement and we already know it's 54. Okay, so right here, this guy is 54. So I also need to now do the integral from 3 to 5 of our velocity function. Once again, the t squared minus 8t plus 15. Okay, so 54 minus 2 times, And we'll do the integral just once more. So, right here is what this guy is, the t, and we'll do from 3 to 5. So we'll do 5 first. And so let me make some room here. So 54 minus 2 times. Okay, let's plug 5 into all these. So 5 cubed is 125. So 125 over 3. 5 squared is, let's see, 25 times 4 is minus 100. And then plus 15 times 5, which is 75. And from that, we're going to subtract the evaluation at time t equals 3. So 3 cubed is 27 divided by 3 is 9 minus, and we've actually already seen these values before, haven't we? Okay, so once we evaluate this, we will know the total distance traveled. Okay, so I'm going to go ahead and grab a calculator to kind of help me out on this part. So we have 125 thirds, and we're going to subtract 100 and add 75. And then here we're going to subtract the 9, add the 36, and subtract the 54. And so I get negative 4 thirds. And I was expecting a negative, right, because we knew it was minus down here. So when I do this, it's going to be 54 plus 8 thirds. Or you could say, what, 56 and 2 thirds is our total distance traveled. Okie dokie. So you can see the difference between displacement and total distance traveled. Displacement, again, was just how far are we at the end from where we began. And then total distance traveled is like how many footsteps did I take in all? Did I turn around? Did I walk backwards? Did I walk forwards? So you can see that the displacement is 54 units, but our total distance traveled is 56 and 2 thirds, which actually means we turned around, but not for very long before we ended up going back to the right. Okay, so there's that part. And let's go ahead, finally, the last piece that I want to talk about is the average velocity of our function. Okay, so once again, we know our velocity is t squared minus 8t plus 15. And I want to know the average velocity that our function takes from 0 to 9 time-wise. Okay, so our average is going to be 1 over b minus a times the integral from a to b of our velocity. Okay, so I want the average here. So let's just go ahead and plug these values in. So it's 1 over, and then 9 minus 0 is 1/9. Of our 0 to 9 of our velocity with respect to t. Well, I've already done this several times. We know this is 54. So 1/9 of 54 is 6. So our average velocity is going to be 6. So when does this velocity occur? So maybe when and where? So time, you have your velocity function right here, which is your t squared minus 8t plus 15. I want to set that equal to 6. So if I subtract 6 from both sides, t squared minus 8t plus 9 equals 0. Let's go ahead and use the quadratic formula on that. So 8 plus or minus the square root of b squared minus 4ac all over 2a. So that's going to be 8 plus or minus, let's see, 64 minus 36 should be 28 over 2. I can simplify this to 2 radical 7 and then cancel some 2's. So 4 plus or minus, what? Radical 7. And that's the time that it will achieve this average velocity of 6. Okay, and the where is going to, just plug that back into your position function, which had a cube and a square with this irrational value like that. Doesn't sound like very much fun. Plus, I'm out of paper again anyway. So you can go ahead and work that on your own. I would encourage you to. And one more thing I'll say about this time. We're between 0 and 9 units. So 4 plus the square root of 7 will be less than 9, and 4 minus the square root of 7 will be greater than 0. So both of these values are okay for where that average velocity takes place. Okay, so there's kind of a thorough examination of a particle motion problem when your particle is moving right and left, kind of back and forth along the x-axis, and we looked at a lot of things. We looked at whether it's speeding up or slowing down. We talked about displacement versus total distance traveled, and we talked about its average velocity and at what time that takes place.